In this little video, I will introduce to you partial molar quantities and one of the most important variables in physical chemistry, the chemical potential. So far, we have been discussing mostly pure substances, but now we will look at mixtures. We will mainly look at homogeneous mixtures where the chemical composition is the same throughout. We will look at non-electrolytes for now, which means there are no ions in solution. This is a mixture such as sucrose in water. During our treatment of mixtures, the component which is smaller in quantity will be called the solute, while the component which has a higher fraction will be called the solvent. These mixtures can also be liquid mixtures and not just solid liquid mixtures. And finally, we will mostly be talking about binary mixtures for the sake of simplicity. Now we know that from the previous videos that pressure and temperature can be used to control the Gibbs free energy. In a mixture, the chemical composition of the mixture or the individual amounts of the different species can also contribute to the Gibbs free energy. And for this we will use partial molar quantities. To understand partial molar quantities, let's take a simple example. Let's say you have 1 liter of water. If I add 1 mole of water to this mixture, the volume of water will increase by 18 milliliters because 1 mole of water is 18 grams and this occupies 18 milliliter. Therefore, after adding 1 mole of water to 1 liter of water, the final volume of water will be 1018 ml. If we repeat the same experiment, but now instead of water we have ethanol, 1 liter of ethanol, and then we add 1 mole of water to 1 mole of ethanol, it turns out that the increase in volume is not equal to 18 ml but is equal to about 14 ml. The reason this occurs is that ethanol, small quantities of water, in this case will be surrounded by large quantities of mainly ethanol, and this changes the behavior of water inside ethanol. So we will define a quantity called the partial molar volume. The partial molar volume of a component in a mixture is the change in volume that occurs when 1 mole of that component is added to the mixture. The most important thing to note is that the partial molar volume changes with composition. It is not a constant quantity. For a mixture containing 2 components A and B, the partial molar volume is defined as the partial derivative of the total volume with respect to the number of moles of component A while keeping the other variables in the system constant. This is the pressure, temperature, and the number of moles of component B. This is the partial molar volume of component A. And you can notice that it depends on the number of moles of A and therefore the overall composition. Now, if I were to add in this mixture a small quantity of A and a small quantity of B while keeping the overall composition constant, then the change in volume will be equal to the partial molar volume of A multiplied by the quantity of A that has been added, and a similar term for B. And this is equal to VA dNA plus the partial molar volume of B multiplied by the number of moles of B that we have added. One can integrate this from 0 to the total number of moles of A. Remember, here we are keeping the overall composition constant, so these two can come out of the integral, and then you have this is how you define the total volume of the mixture. If you plot for such a mixture the volume versus the number of moles of A, for example, you might get something like this. And the partial molar volume of A is the slope of this curve at different points, and you can see that it's different. So here the slope will be something like this at this point. So let's call this point A. At this point, on the other hand, the slope will be like this. And you can clearly see that the slope at point B is negative. So the partial molar volume of A is negative at the point B. So at this composition, if you add a little bit more of A to the mixture, the overall volume will actually decrease. So the molar volume, which is simply equal to the number of moles divided by the total volume divided by the number of moles of A, is always a positive quantity, but the partial molar volume can be a negative quantity. One example of this is if you add magnesium sulfate to water, the volume of water actually decreases. The volume of the solution decreases. And the reason this occurs is because magnesium sulfate forms ions, and these ions disrupt the free structure of water and they get hydrated. So magnesium ions will now be surrounded by water molecules, and therefore the structure of water will collapse a little bit, resulting in a small decrease of volume. The chemical potential, which we will define now, is the partial molar Gibbs free energy in a mixture. And it is defined in the following way. The symbol is mu. The chemical potential of mu is the partial derivative of the total Gibbs free energy with respect to the number of moles of A, while keeping the temperature, pressure, and the number of moles of B constant. Remember, we are talking about a binary mixture here. So if I were to plot the Gibbs free energy as a function of the number of moles of A, I might get something like this. And the slope of this curve at any point this was not correct. I will redraw this. The slope of this curve at any point will give you the chemical potential at that point or that composition. So what is very important to note is that chemical potential varies with composition. So the fundamental equation of chemical thermodynamics, which was previously written as in this form, can now be modified and be written in its more complete form. Earlier we only had contributions from pressure and temperature for pure systems, but now we also have contributions from the chemical potential. and this will be written in the following manner. Assuming it's a binary mixture, if there are more components, then there will be more terms like these. Just like the name suggests, the chemical potential of a substance is the potential or the ability of that substance to change the overall Gibbs free energy. So if mu A is very high, its contribution to the Gibbs free energy will also be very high. And therefore, this also tells you how different components as a mixture can control equilibrium. For pure substances, let's say for a substance J, the molar Gibbs free energy is given by the Gibbs free energy divided by the number of moles of J. But if the substance is pure and there are no other components in the system, then from the previous definition of the chemical potential, this will be equal to the chemical potential. So this equation, where the molar Gibbs free energy of J is equal to the chemical potential of J, applies to pure systems, single component systems. There is a wider significance of the chemical potential. It can also be shown, for example, that the chemical potential of a substance is related to the internal energy of the substance while keeping the entropy, volume, and the number of moles of the other substances constant. So it also shows you how internal energy and similarly the Gibbs free energy and the Helmholtz free energy, how these depend on composition. In the next part of this lecture, we will analyze the variation of chemical potential with partial pressure and the condition for equilibrium in